All right, Alexa, pause. All right, so today we're going to do this lab that basically allows us to determine the R constant. This little piece is called a UDometer. This is one of the more expensive things that we have in the laboratory. You can see it is that expensive because of these amazing gradients that it has. Is it going to refocus it? Let's see if I can remember which button might do that. Yeah. So you can see that this actually goes out 2 decimal places versus a lot of our graduated cylinders, especially our 100 milliliter graduated cylinder, only goes at 1. So we're getting an extra digit here, which is kind of important if we're trying to solve for something that's like 0.088, 0.0821. So that extra digit is going to make our answer more accurate or closer to the true value. So we've got this. We need a piece of magnesium because we are going to produce hydrogen gas today. So if we come over here, I'm going to clip off a piece of magnesium. Then we're going to take a look at its mass. So we're zeroed. We put that on there. The mass of this is 0.087 grams. So that's the mass of the magnesium. That's pretty important. 0.087 grams. Actually, I'm going to pause this. I actually have a different scale. I'm going to actually try something. All right, so just for some stupid fun, this thing is ridiculous, and you can see how many decimal places this thing goes out to. So just to give you a quick glance, we are going to, since I'm the only one doing this, let's just see what we can get here. So this thing is oh, well, that didn't help anybody, did it? Let's see here. So let's make sure. We're going to have to re-zero that, I think. All right. So let's try that again. I'm going to have to put it, bend it a little bit. I'm going to put that right on there if I can. Oh, that's amazing, right? So we got 0.087 on our other scale. I am going to go ahead and close these doors, but I'm afraid that it might move that magnesium. Let's see. All right, very cool. So we're going to go with this. And this is it's kind of amazing because now we've got 4 significant digits. 0.08699, which is so funny, right? But the cool thing is we get those extra digits. It's going to jump a little bit because I'm actually going to write on the table it's sitting on. So you're actually going to see it move a little bit. Oh, wow. Well, that could be dust fragments getting on there. So let's go ahead and keep that 699 because as soon as I touched the table, it actually did that. That could be, fragments or whatever that were in there settling on it now. So we're going to keep that as 0.08699. Even though this says that, write it down as 0.08699. All right. Yeah, and see, looks like some dust has actually stayed on there. Let's try this one more time. Let's do it a little quicker. And let's get it right there. Sorry about that, but it must have been some particles that settled on it. So 0.0694. And we're going to take that, and as you can see, it's going to go up because particles are going to start settling on there, and that's going to adjust it. When we're going out this many decimal places, it is pretty crazy. And there is a draft in this room. So just to make sure everybody's clear on that, 0.08694 is the mass that we have for this guy right here. Cool. So that's a lot of decimal places. I'm pretty excited about that. I'm really excited. All right, so we're going to take that piece of magnesium and we're going to curl it around a piece of thread. So normally one lab partner would be doing this, while the other one goes over and fills up the barometer with 10 milliliters of the most concentrated acid that we have. So I need to stick this through here, and then I'm going to tie that. I wish I was a little bit better at tying things. That should be good enough. All right, so since we've got this time, let's go ahead and get the pressure, and then I'm going to fill up the burette, not the burette, the eudiometer with the acid. So let's take a look there. Temperature is set up and lined up with it. And then we look down here. Looks like we're at 776, 777.8 now. So 777.8 for the barometer. Now, this thing over here, this is called the fume hood. We want to turn a light on in there so we can see, and we want to power up this so this takes all of the gas out. So now that's actually removing the gas. That way the vapors from the hydrochloric acid are not going to hurt me. Hopefully, if all of that works okay. So I'm going to pause that now and then just show it to you in a second. So at this point, I do have the highly concentrated HCl in here. You just have to have at least 10. 10 makes that HCl the excess reagent. So that means the magnesium will definitely be the limiting reagent. And all I'm doing is pouring water over this so I can get it all the way full. The HCl actually stays at the bottom because it's more dense, but I do want to tap any air bubbles off the side of that. I need to make sure that this is completely filled. Alexa, pause. Alexa, pause. I'm going to take, I'm going to do it this way a little bit. So I'm going to take this magnesium and I'm going to stick it in there. It's not going to react because all of the actual HCl is down at the bottom. I'm going to hold on to this with my thumb so that it doesn't fall all the way down to the bottom. And then I'm going to put this in, water squeezed out, so that means that it should be completely gasless. I'm going to tip this over and drop it in with my finger. I've got to get my finger below that level so that there are no gases that trap up. And I'll know in a second if I succeeded. I don't see any bubbles up here. So that is really cool. So I'm going to let you guys see this reaction. And what you're going to see how there's no bubbles at the top? That is really good. That's just stuff on the outside. But now I'm going to put you down here so that you can see whenever that magnesium, whenever that HCl, which is more dense, drops down here and touches that magnesium, we're going to see that react and form. Well, you should be able to predict what it's going to form. Oh, there it is. It's forming on the outside of it already, just a little bit. I wish that plastic was a little clearer for you guys. It stinks. But now you can actually see those bubbles. Very cool. And I will bring you back down to that, but take a look. Slowly but surely, hydrogen gas is filling up this tube. I'm just going to put it right here so you can see it all. You can actually see it's already gotten past the level in the water. So I'll move this over here. That's all hydrogen gas. You can see, maybe you can't. You can see that all we have left here is a ring of thread. That means all of our all of our magnesium is gone. So let's take a look here. If this water level right here is above, notice if I keep pulling it out, it goes down. That's because the pressure in this tube is less than atmospheric pressure. If I push this down, you can see, hopefully, I'm not sure if you can. Maybe I need to zoom out a little bit. But what you're going to be able to see is that the water level on that goes up. If we're up here, it goes down. If we go down into the water, it goes up. That's because the deeper down it goes, like I said before, the deeper down this goes, the higher the pressure, right? So to get the pressure inside here equal to the pressure on the surface of this water, we've actually got to layer these right up with each other. And what I'm going to do is I'm going to add a little bit more water so that you guys might be able to see that. So right there, those two water levels are the same. And that's when I'm going to take my reading of that gas in there. So I want them to be the same, and it's 88.18. 88.18. This is milliliters. The other thing we need for PV equals nRT is we need a temperature. So we're going to put this into here. A student of mine once dropped this in there. It did not survive that. So I'm going to be careful that I can show you what it says, but also keep it not flowing in there. But 23.5, 23.6. Try to give it 6 or 7 seconds to stay. Now that is colder than the room, so we want to make sure that that we take it. Let's go with 23.8 going once, going twice. So 23.8. Let's just make sure that it is the same here. Yep, 88.18. 23.8 for the temperature. And you should already have the wow, that's close. I zoomed in. You should already have the barometric pressure, and keep in mind that we did collect this gas over water as well. So that means that you'll have to subtract the vapor pressure off, like we did with the combined gas law. That will give you the accurate pressure. So with that known, that should be enough for you to go down through and answer these calculations, and then answer the questions as well. Thank you, and let me just make sure. Pressure, you've got to subtract the vapor pressure, so that will give you P. Volume, we've got the volume, 88.18. Temperature, we've got the temperature as 23.8. You might be asking yourself, well, where do we get the number of moles? Well, remember, we know the mass, I'm pointing over like you know where that scale is in my room. We know the mass of the magnesium, and by the use of stoichiometry, we should be able to figure out how many moles of hydrogen we could use if all of that magnesium were to be used up during the reaction. So that should be enough to get through everything. Real quick, don't forget to change your temperature to Kelvin, otherwise you'll be very upset. And remember, we will have millimeters of mercury, but we want to calculate this versus 0.0821. So we also need to change our pressure from millimeters of mercury to atmospheres. All right, excellent.